numerical descriptive measures. And last class we started talking about the central location or measure of central tendency. And then we went into discussion of scatter or spread or standard deviation. I believe we were talking about standard deviation at the end of last class. Okay, right. So this is how you calculate the standard deviation. But of course, before you start calculate the standard deviation, you have to calculate variance first, right? Because standard deviation is simply a square root of variance, okay? And I believe I showed you how to do that in Excel, right? So you should be able to do that by hand for small numbers like this for your exam purpose, okay? But for most of the practical purpose in your research or whatever in your project, okay, chances of the data size will be pretty large, and the calculating standard deviation or variance by hand may become very tedious work. Okay, so I would suggest you use Excel, or actually there are many other statistical software that allow you to do that. Okay? If you have any access to other software, that's fine. Okay, so this just a summary of what we've done regarding the standard deviation. Again, the standard deviation and variance are measures of spread, how widely the data points are scattered. Okay? So here we have 3 illustrative graphs or charts here. So we have the data points scattered from 11 through 21, and we have this kind of distribution. Okay? The second one, we have data points scattered mostly in the center. The last distribution have pretty much similar range as the first one, starting from 11 to 21 or 11 to 20. So the range would be what? What's the range for this distribution? What's the range for this distribution? 10, right? 21 minus 11, right? You need this startup to start thinking, right? All right. Well, for this one, the range would be 9. So there's a slight difference in range, but almost the same, right? Well, obviously this one, the range is pretty small, right? So if you actually calculate standard deviations based on these 3 different data, you would see something like this. Okay? So of course, the means are all the same. They created the data scatter deliberately that way. Okay? But if you get 3.338, for example, for standard deviation for this distribution, right? Then the standard deviation for the second distribution would be much smaller because you have narrow distribution. I mean, all the data points are scattered within the very narrow range. Okay? But for the third distribution, what's the difference between first and third? As I mentioned already, the ranges are pretty much the same. But do you see any particular difference between those 2 distributions? How would you describe the difference? It's hard to speak in English, right? Explain in English. But go ahead and try. What's the striking difference between the first and third distribution? Number of modes? Okay, yeah, modes are different, yes. Because here we have 2 modes, right? 11 and 20. And here we have only 1 mode, right? That's true, right? But what about just the shape of distribution? Regarding the shape of distribution, what do you see? Huh? If the first distribution, I mean, if we use a curve, right, it may look like this, right? Because just a little bit of mound or the bar in the middle, right? But for the third distribution, you know, it's almost like this, right? So we have a striking difference in the shape of distribution between the two distributions, right? Or if you have that, then you're going to get quite different measures of standard deviation. Okay? So even when the two distributions have this almost identical range, okay, depending on the actual distribution shape, right, you're going to get different measurements of standard deviation. The standard deviation will come out much larger because we don't have any observations in the middle, right? But the observations are scattered widely apart. Okay. Okay. And this is just another way to show the distribution. Okay. So I think last class I told you about the this kind of curve. Actual name is probability density curve, or PDF, probability density function. Okay. And if you have smaller standard deviation, that means the distribution is narrower. Okay. So larger standard deviation represent the wider and flatter distribution. If, again, we are ahead of ourselves, so we're going to talk about the continuous distribution probability and actual normal distribution in chapter 6. At that time, we will discuss more in detail. But if you have any distribution which is wider, it will necessarily be lower, flatter. Okay? If you have any distribution which is narrower, it will be high, like this. Okay? Any idea why it would have been that way? Well, again, it's too early, but the reason is the total area under the curve must be 1. Okay? Because from here to here, each distribution covers all possibilities. Okay? So if you add up the probabilities of all possibilities, it has to be 100%. Right? So the total area under the curve must be 1. Okay? So if you distribute the 100% within wider range, then it will necessarily have to be lower. Okay? Within the narrow range, wider range or narrow range, I guess you'll have to squeeze it up, right? So that's why the distributions look that way. All right, so just a few summary points of characteristics, okay, of variation. The more the data are spread out, greater the range, variance, standard deviation. Vice versa, right? If the data points are more concentrated, right, then the smaller the range, variance, and standard deviation. If there is no variation, if the data points are all the same, it will be highly unlikely that you will have that kind of data. But in case you have the data points with all the same numbers, then everything will be 0, right? Range will be 0, standard deviation, variance will all be 0, okay? Because there is no variation. Okay? And none of these measures are ever negative. They are all positive, always positive. Okay? But first of all, variance, the formula, summation of something squared divided by either n minus 1 or n, depending on sample variance or population variance. Okay? So if you square something, right, it's all positive, right? And add them up the positive numbers and divide by whatever the number you have, right? Always positive. So that's variance. Okay? If you take a square root, standard deviation will also be positive. Okay? Just keep that in mind. So in your calculation, you get negative number, you should know you messed it up, right? You did something wrong. Okay? All right, so let's talk about one more measure of variation, that is coefficient of variation. And this is, relatively less frequently used measure compared to standard deviation or variance, but it's still a very popular measure of variation. Okay? This is how you calculate coefficient of variation. You divide the standard deviation by the mean, okay? And then you multiply 100 in order to make it a percentage, okay? So in other words, it's just simply the ratio between the standard deviation and the mean. Compared to the mean, what's the standard deviation, okay? So it is relative measures of relative variation, always in percentage, okay? But another use of the coefficient of variation is you can compare the variability of two or more sets of data measured in different units. Okay? So not only you're comparing the two data sets in the same measurement, same units, whether it's centimeters or kilograms or whatever, right? You can actually compare and you can make meaningful comparison between the data sets that are dealing with the completely different units, okay? We'll talk about those examples now, okay? So here we have some examples of actual coefficient variation, okay? Let's say you are interested in investing in stocks, okay? And when you take a finance course, you will learn that what they mean by risk in finance is nothing but uncertainty or variation. If something is uncertain, something has a lot of variability, then in finance we call that risky. So financial market really hates uncertainty. If there is any incident, whether it's a political or economic, something that happens that brings some uncertainty in the market, then the stock market drops immediately, right? So right now, the crisis in Ukraine or Crimean Peninsula, right? Those things have been hampering the stock market for a few weeks now, okay? Well, I think it's almost settled now, so the stock market has been recovering the last few days. Okay? If you have anything that brings some uncertainty, like unemployment rate, okay? Whenever the unemployment rate is announced, if it went up, then people think, well, what's going to happen to the economy? Okay? So unemployment, the stock prices tend to drop. Okay? All right, so the first thing you have to find out if you want to invest in any stocks is how reliable these stock prices are, right? Or what kind of uncertainty do these stock prices have, right? So here's an effort to answer those questions, right? So let's say we have two different stocks, A and B, and let's say two stocks have equal standard deviation, I guess, based on the past history in the data, right? We calculated their standard deviation. We found out both stocks have $5 standard deviation, okay? Does that mean they are equally risky or equally variable, right? Well, you have to compare that to the average price. So here we have one more piece of information. Average price last year for stock A was $50, but average price last year for stock B was $100. Okay? So when you compare this variability, the changes that occurred in the stock prices during the last year or in the past, okay, compared to the average price, then we find very important information, right? In the first case, $5 divided by $50 is 10%, right? So compared to the regular or average price, there was about 10% fluctuation in the stock price, which may be an indication that it can continue in the future as well, right? Well, we make a prediction or forecast based on the past history, right? So you have to expect about 10% fluctuation in this particular stock. But in the case of stock B, it's only 5%. Even though we have the same $5 standard deviation, when you compare it to the average price, it's much smaller, only half the variability of stock A. Okay? So that's one example. In the second example, we have two different, completely different average price. Okay? But if you look at just the standard deviation, stock A has $5 standard deviation, but here we bring another stock, stock C, right, has only $2 variation. So if you just look at the standard deviation, you can conclude that, well, stock C is much safer or less risky because standard deviation is very narrow, right? Or there was only $2 variation among the stock prices, right? But when you compare that to the mean value, then you get completely different picture, right? Again, for stock A, that $5 standard deviation amounted only about 10% of variation, right? But in case of stock C, that $2 variability represents whopping 25% of the variation, right? So compared to $8, $2 variation is quite a significant fluctuation, right? So you should conclude stock C is a lot riskier than stock A. In other words, if you, let's say, you have $10,000 to invest, right? So if you invest $10,000 here in stock A versus $10,000 in stock C, right? After a year, what you can expect is either you end up with $11,000, the total asset value, or $9,000 total asset value. Do you understand what I mean, right? If you invest $10,000 right now, according to this measurements of 10% coefficient variation, right, you can expect, well, if you're lucky, right, you can end up with 11,000 here. But if you are unlucky this year, if the economy is bad, stock market doesn't perform, then you can end up with $9,000 asset value, right? However, in case you invested $10,000 in stock C, what should you expect? Right? Right. Can you say exactly how much? If you're lucky, you can have up to 25% appreciation, right? So what? About 12,500. You can end up with $12,500 asset value, right? But if you are unlucky, your asset value can go down to almost $7,500, right? You can lose 25% of the value, right? So that's the idea. In finance, this variation, well, you can, if you are an optimist, you can say, hey, I can make a lot more money, right? But in finance, it is considered risk, right? The high variability is considered risk, right? Okay. Here's another example. You don't have this in your note. I just copied it from the textbook. Okay? This is textbook example 3.7 right, in your textbook. Okay? And this is the case where they deal with the two data sets with completely different units, right? So if you read the question here, which varies more from cereal to cereal, the number of calories or the amount of sugar in grams? I think this I don't think it's projectors. Both projectors are doing the same thing, right? So maybe it's a computer somehow. All right, so let's say you have two different boxes of breakfast cereal, okay, or two different brands of breakfast cereal, and maybe you are asking, what's the difference in the number of calories, okay, or sugar contents? Which one varies more? Okay? So you can calculate the coefficient variation in calories, coefficient variation in sugar, okay? Suppose, well, apparently somewhere in the previous examples, they calculated standard deviation and the mean, right? Standard deviation and the mean, right? Or here they are given, right, for the second sugar content, okay? Oh, okay, so what's the conclusion? In which measurement do these two cereal boxes vary more? Which one? Sugar content, right? Rather than calories, right? So compared to the average calorie figure, right? The difference between the two, the variability in calories is only 36%, right? But in sugar content, there is more than 50%, almost 60% difference in sugar content, right? So this is an example of the case you can make some meaningful comparison in two different data sets with completely different measurements, okay? Okay? Any questions so far? Okay, so we are about 2/3 done in this chapter. Remember, in the beginning of the chapter, I gave you this notation, right? And this is a very succinct way to present an information about any distribution, right? And what this means is there is any random variable x, and this variable is distributed normally with the mean value of mu, or whatever certain number. It could be 1 and 0, right? Or 0 or 1. Right? If the standard deviation is 0, that means we have just one number, one single number for the data, no variation. Okay? Anyway, so we talked about the central location so far and the variability. So now we are going to talk about the shape or type of distribution. Okay? What type of distribution do we have? Okay? And regarding the shape of distribution, there are two popular measurements. Okay? One is skewness, the other is kurtosis. Okay? In Korean language, those are not very frequently used names. The skewness is called wado, right? Kurtosis is called is translated into chamdo, right? And I didn't know this until last year. Right? I told you I never learned the statistics in Korea. Okay? So last year, after I came back to Korea, I learned this Korean names of these concepts, okay? Through Excel, actually. Okay? All right, the skewness measures the amount of asymmetry in a distribution. Okay? How the distributions are different or away from symmetric distribution. Okay? So here we have three different types or or different skewness or symmetry of distribution. Okay? Well, of course, the one in the middle, you can say the distribution is symmetric, okay? Equal on both sides. Okay? If you have any distribution like this is what we're going to call left-skewed distribution, right? But what do you see here? In what cases, in which cases do we call them left-skewed? How would you describe this distribution? How would you describe? Do you see more observations on the right side or left side? I think I hear both. Huh? I think I'm asking a wrong question because what do you mean by right or left? Where is the center, right? Well, the way we describe this kind of distribution in statistics is we say this distribution has a longer tail on the left side. Longer tail on the left side. Okay? What that means is actually you have some extremely small numbers compared to the usual numbers within the data set, right? Let's say about, I would say 80–90% of the numbers are found within this range, right? But you have some very small numbers on this tail, on the left side, right? Extreme small numbers, right? And that's what we mean by longer left tail or longer tail on the left side, okay? So it seems a little counterintuitive to me, right? I mean, if I look at this, first time I looked at this distribution, I thought, well, most numbers are found on the right side, okay? And very few numbers on the left side. So I actually I had an inclination to call this right skewed, okay? Because it looks like the distribution is leaning towards the right side. Okay? But remember, the name goes with the tail. Okay? If you have a longer tail on the left side, we call it left skewed. Okay? Make sure you understand that. Remember that, right? It depends on where do you see the longer tail. If you see the longer tail on the left side, we call it left skewed. Okay? And the characteristic of the left skewed distribution is mean, which is this blue line, is less than median, which is the red line here. Okay? Mean will be less than median. Okay? Try to think about it. Try to understand why. How do you know? Why would that happen? If the distribution has a longer tail to the left side, or what that means is we have extremely small numbers, right? Then mean will be less than median. Can you explain why? It's a very simple answer. There's a very simple answer. We talked about it last class. One very important characteristic of mean. Outlier, right. Means are sensitive to outliers, right? Means are easily affected by extreme observations, okay? So when we have extreme small numbers on this side, that tend to bring the mean value towards that side, okay? So mean values are affected by extreme small values. That's why mean value will be less than median, okay? Well, if the distribution was symmetric like this, right, then mean would be equal to median because, we have equal number of distribution on both sides, right? And so it's easy to understand it that way. Right skewed distribution is the opposite case. We have longer tail on the right-hand side, okay? And then we call it right skewed, okay? And that means you will see some extreme large numbers in this distribution, right? There are some extreme large numbers, okay? And naturally, that will bring the mean value towards that larger side, right? So mean will be larger than median in that case. Okay? Make sure you understand the different shapes of distribution, right? As far as symmetry goes, okay? Now, skewness is a measurement. It is a designed measurement to represent these shapes of distributions by a number, okay? So if you calculate skewness using the symmetric distribution, you will get exactly 0 as a measure of skewness, okay? In case you calculate the skewness with the left skewed distribution, then skewness value will come out to be less than 0, negative number, okay? And the right skewed distribution will produce positive number for skewness measurement. We have two different colors here. Okay. Anyway, so I'll show you exactly what Excel does with these measurements in a few minutes. Okay? The other measurements regarding the shape of distribution is kurtosis. Okay? Kurtosis describes the relative concentration of values in the center as compared to the tails. Right? So basically, it's a measurement of sharpness of the peak right? If there is any peak in the data, right? How sharp is the peak, right? So in this case, this is actually what we call uniform distribution, right? There is no peak here, right? All the points are evenly distributed. All the data points are evenly distributed, okay? Well, in that case, if you use kurtosis statistic, if you calculate kurtosis measure, you will get a negative number, okay? If you have something like this bell-shaped or mound-shaped distribution, okay? In other words, you have some peak, right? You have a peak, but the peak is not really pointed, right? Then you'll get something close to 0 for kurtosis measurements, okay? If the peak is really sharp, really pointed like this, so it's narrow instead of wide and even distribution, you have very concentrated distribution in the middle, right? Then the kurtosis measurement will be positive number, okay? So again, now we are talking about the numerical measurements about distribution, right? So without actually looking at the shape of the distribution, by looking at these two numbers, right? You should be able to guess, right? Get some ideas on what the shape of the distribution will be. Okay, so these are those are the ideas of these two measurements. Okay, all right. So next couple of slides show how to use or how to look at the data in Excel and actually get these measurements, right? And there are many different calculations. Of course, you're starting from the mean. You can calculate the standard. Well, standard error we didn't talk about yet. Okay, we'll just keep maybe a couple of weeks. Okay, but we know how to the concept of median, mode, standard deviation, variance, kurtosis, skewness, range, minimum, maximum, sum, the total sum, summation, and the number of observation. Okay. In Excel, there is a function that easily calculates all these measures immediately, quickly, at just one command. Okay? So let me show you how to do it. Okay. And let me just recreate this simple measure, let's say 2 million. And what is it, 500,000? 300,000. Oops. And 100, 100. Is it 100, 100? Okay, so we have this data, right? Just to recreate what we see in the PowerPoint presentation right here, right? So once you have the data, what you can do is just go to data analysis, and here's another story. You know, first time I was teaching at Hanyang University last year, right? I couldn't find this thing because, again, my computer has an English version of Excel. And what the descriptive statistics in English is called the 기술통계법 here. Right? But when I first saw this, I thought 기술 meant technology. Right? So what does that mean by technology or technical statistics? But eventually I realized that this means descriptive statistic. Okay? So choose this one and go OK. And you highlight the range. In case you included the label, just check here, check this box for label. But we don't have any label here now. And then you can choose, where you want your output. Let's choose here. Okay, let's say. And then you make sure you check this, summary statistics. Okay? And later, you may need to do this later, but let's forget about it now. Okay? And click OK. Yeah, that's it. So it already calculated all the numbers here. Okay? So mean value is 600,000. Standard error, again, don't worry about standard error now. Okay? The median, mode, standard deviation, I believe that's sample standard deviation instead of population standard deviation. You can quickly check here. Oh, it doesn't show the formula, it just shows the number. Okay? But I'm sure that's a sample standard deviation. I think right here, so sample variance, okay. Or standard deviation and sample variance. Yeah, right. So it says sample variance. I'm sure this is sample standard deviation. You can verify it if you like. Okay. Here, some of you may have not seen this expression, right? 6.4 e to the plus 11, right? This is how we write a very large number or very small number, okay? Because obviously, we have a limited space here, okay? So what this means is 6.4, and we have this first digit of 6.4 is 11th digit above the decimal point, right? So we have yeah, that's right, right? Right? So here's the decimal point, okay? And this first digit is 11th digit above the decimal point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? So because it's, number is very long, right? Instead of writing that number out, right? This is what we call scientific notation. In science, we use this notation, right? E to the plus 11, right? Well, sometimes you will see negative 11, okay? If you see negative 11 or negative 5, let's say you had 6.4 e negative 8, okay? And what that means is the first digit here is the 8th digit below the decimal point, right? So this is actually 0.000000064, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So what that means is that first digit is 8th digit below the decimal point, right? Make sure you know how to interpret this expression, okay? All right, 첨도. That's kurtosis, okay? Kurtosis 4.13. What does that mean? If you have a positive number in kurtosis, what can you say about the distribution? Is it relatively flat or relatively narrow and pointy? Narrow and pointy, right? Yeah, if you look at this distribution, it's pretty, narrow and pointy, right? I mean, there's one number pretty large, 2 million, right? So if you have 100,000, 5, 10, 15, 20, right? Almost the distribution is something like this, right? We have one very extreme large number. Here's 0, 500,000, 1 million, and 2 million here, right? So the distribution looks something like that, right? Am I right? No. I think I'm confusing here. Okay. So we have two observations in right here. Up, up, and 3. So we have 1 here, and 5 here, and right here. All right, sorry. So it's something like this. Make sure I'm doing it right, right? Yeah. That's kurtosis, right? How about skewness? Skewness 2.0068, right? Again, we have a positive number, right? And so what does that mean? If you have a positive number for skewness, is that left-tailed or right-tailed? Left skewed or right skewed? Right skewed, right? As you see here. We have a longer tail on the right. Okay. Okay. Range is 1,900,000, yes, because it's just 2 million minus 100,000. Okay. Maximum, summation, total summation, minimum, maximum, and the total number of observation. Okay. Count is 5. All right, so that's how you use descriptive statistics to easily figure out the characteristics, many different characteristics of a data set. Okay? Very useful in many cases. So before you, whenever you do any data analysis, you should use this descriptive statistics first to gain the quick grasp, quick understanding of how the data points are scattered. Okay? That's typically what we do as a researcher. Okay? All right. The next concept is still, we're talking about the different types of distribution, right? The shapes of distribution. And we introduce a new concept with quite frequently used concept here. It's called the quartile. Okay? Quart or quarter, represent 25% or 1/4. Okay? So quartile measures means where is the 25%, right? Where is the bottom 25%? Where is the top 25%? where is the second 25% and the third 25% of the data points. Okay? So first quartile is the value for which 25% of the observations are smaller than, and 75% of observations are larger than that number, right? Q1, first quartile. It has 25% below, 75% above that number. Okay? Well, second quartile is 50% below, 50% above. And we talked about this last class, right? That's exactly the definition of median, right? If any number has 50% below, 50% above, right? So second quartile is always equal to median. Okay? And then third quartile is a number which has 75% below, 25% above. Okay? So when you calculate these three quartiles, Q1, Q2, Q3, by looking at the magnitude of these three measurements, you can quickly get the idea about the shape of the distribution. Okay? How? Well, before we talk about how, let's first talk about actual calculation of quartiles. Last class, we talked about how to calculate the median. And in order to find actual median, you have to calculate the position number first. Right? Position first. So, excuse me. Depends on whether you have total even numbered observation or odd numbered observation. It's slightly different, right? So it's the same idea goes here, right? In order to find actual quartiles, you have to find the position numbers first, okay? And the first quartile, the position or rank is n plus 1 divided by 4. N plus 1 divided by 4, okay? And second quartile, which is median, which this is exactly the same as median formula, as you've seen last class, okay? And here, the third quartile, we use this formula, 3 times Q1 formula. 3 times Q1 formula, right? Of course, because third quartile is 3 times as large as the first quartile, I mean, in terms of number of percentages, okay? So let's say, here are some examples. Okay. Here are actual examples of the data points. We have 9 numbers here, 11 through 22, right? So in order to find out the first quartile, you would do 9 plus 1 divided by 4, and you got 2.5 position. So what that means is that particular number which is located at 2.5 rank, or 2.5th number, right, is the first quartile, right? So in that case, what you're going to do is, well, obviously the first quartile is between second number and third number, so you're going to take an average, okay? So the average is 12.5. That's your first quartile. Okay? The second quartile, it comes out exactly 5, right? So 16, that's your median or second quartile. Third quartile, according to the formula, you come up with 7.5, okay? So again, that means third quartile number is between 7th number and 8th number. So you're going to take an average of 7th number and 8th number, which is 19.5, okay? Well, there can be some slight complication here. Here. Well, let's start with this. If the position number calculation comes out to be fractional half, exactly 2.5, 7.5, 8.5, something like that, right? Then you're going to take an average of 2 numbers, right? If it's 7.5, take average of 7th number and 8th number, right? However, it's possible that that calculation can come up with, say, 7.2. or 7.31, right? Depending on what, how many number you have, right? So in that case, you're going to do round up, okay? Round to the nearest integer, okay? So if it comes out to be 3.26, then it's going to be 3. So you take third number as quartile number, right? If you have 11.2, 11.71, right? Then you round it to the nearest integer, which is 12. Okay? All right? So that's how we're going to find the position or rank of quartile numbers. Okay? Is it clear? Any question? All right. And let's try to go ahead. So, based on what we have discussed so far, that is what's called the 5-number summary. Many times, when you have a data set, in order to present the data, the characteristics of the data to your audience, right? Well, in chapter 2, we talked about the visual presentation, in table, charts, graphs, right? But in chapter 3, we're talking about numerical presentation, right? And we talked about many different numerical measures, right? But many times we use this 5-number summary, right? By presenting these 5 numbers, we can give or we can convey very quick ideas about a data set to your audience, okay? So those 5 numbers are smallest, largest, first, second, third quartile, okay? If you present these 5 numbers, then you should, the readers, your audience should get pretty good ideas about the shape of the distribution. Here's how. Okay? So let's say we have some number between 12 and 70. I don't know how many numbers. Doesn't matter, right? Okay. But suppose you presented 5 numbers. Minimum, first quartile, second quartile, third quartile, and the maximum, right? So first of all, you can easily, the readers can easily calculate the range, right? Get quick idea of how widely the data points are scattered, right? And then, by looking at the median, okay, they can also get the idea of whether the data are left skewed or right skewed, okay? Obviously, 45 is slightly to the right of between 12 and 70, right? And that means about 50% of the distribution, 50% of the data points are between 45 and 70, right? Which is 25, right? Between 70 and 45, the distance is 25, right? So within the range of 25, you have half of the distribution, right? But on the left-hand side, right, the other half of the distribution is found between 12 and 45, right? So that range is about 33, right? So it's slightly wider than this side, okay? So what that, from that you have the idea, it's slightly, is that skewed to the right or skewed to the left? Skewed to the left, right? Did I say it wrong? I think maybe I said it wrong first time, right? Anyway, so by looking at the median, we can get that idea, right? And even beside that, even more than that, right? We have, by looking at the Q1 and Q3, we can get more exact ideas about the distribution, right? And using this box, okay, we, many times we represent the first quarter, the first quartile and the third quartile, okay? So that's how we use 5-number summary, all right? the range between Q1 and Q3 has a special name. It's called the interquartile range. Interquartile range. Okay? Interquartile range is the area where you find the middle 50% of the observations. Right? So, we have, this is the middle, the center, and you have 50% to the left, 25% lower than that number, 25% larger than that number. So the total of 50% of the observations are found between first quartile and third quartile. And that range is called the interquartile range. Okay? So let me ask you this question. If you have two different cases, in the first case we have 27 for interquartile range. We have another data, okay? Similar data, but that data has an interquartile range of only 17 instead of 27, right? What can you say? Largest what? Standard deviation? When you say second one, the one with the IQR of 17. 17. So we're talking about 27 versus 17. Suppose we have another data set here. And we have, okay, and this IQR was only 17, right? So that, forget about anything else, but that particular IQR difference, 27 versus 17, right? What information do they present? What can you say quickly about the shape of the distribution? All right, let me give you multiple choice. Which one is which? Left one is what? 27, right? And this is 17, right? Because IQR means you find 50% of the middle 50% of the observations, right? And here, middle 50% observations are distributed within the range of 27, right? So something like, right, here, that's 27, right? But here, middle 50%, we scattered within the range of 17, pretty narrow range, right? Which means the distribution will be pointy, 첨도, right? Sorry, I keep telling you Korean name, right? Kurtosis. There is a difference in the measure of kurtosis between the two distributions, right? Okay, so that's, by looking at the interquartile range, you can quickly get the idea about kurtosis, or how concentrated or how widely scattered the distribution is, right? Okay. And based on this idea, there's what's called the box plot. Box plot. And this is a very widely used graphical illustration or visual presentation about a data distribution, right? And that's exactly based on 5-point summary, right? We have box here. The center line is median value. Here's the first quartile, third quartile, and then the smallest value. We extend a line towards the smallest value, and another line on the right-hand side towards the largest value. So we mark this with, many times, depending on what software you use. Some software something like this. Instead of bar, vertical bar, they mark with an X. Okay? A lot of software you can create actually vertical box plot. Okay? And many softwares, they call this box and whisker. Box and whiskers plot. You know whiskers? Okay. So these things are called whiskers. Okay. So what's the role of whiskers? What do they show? Depending on how long the whiskers, right? You can get the idea about how extreme, what kind of extreme values you have in the data set, right? And apparently here, again, you have a long tail on the left, right? So this is obviously a left skewed distribution, okay? Okay? If you read the chapter, I didn't check the 7th edition yet, but I'm pretty sure you find the same thing. Excel, unfortunately, doesn't have a function to create box and whisker chart. Okay? If you search on the web, some people created some programming, right, that you can use to create box and whisker chart using Excel, right? But that's not really the formal official version of Excel software. Okay? So, well, in case I ask you to create box and whisker chart, you can do that by hand. Okay? All right, so here, just an illustration of the typical shapes and representing box plots. Okay? If you have left skewed like this, okay? Obviously here's the median, Q1, Q2. Okay? And where will be the mean? Again, do you remember mean? Mean will be less than Q2, right? And here, mean will be greater than Q2, because again, mean is affected by extreme values, right? So it goes move towards the extreme value side, okay? All right, so here's one very simple example of box plot. Yeah, I think this is going to be our last slide today, okay? All right, so we have this distribution. We have one very extreme large value, 27 here, right? So in that case, if you calculate the Q1, right, using the formula, you find out number 2 is Q1, and number 5 is Q3. So this number 5 has 75% of the observations less than that number, right? So obviously we have, by just looking at this box plot, right? You can see there is an extremely large number, outlier on the right-hand side, okay? And that's a right skew distribution. And it's a very long tail, right? Long tail on the right-hand side, okay? All right, any question? We have just one concept left in this chapter. We're going to finish that on Tuesday. And we're going to go to chapter 4. We're going to get into chapter 4 on Tuesday, even though it's not covered by first exam. So make sure you read ahead. All right? Okay, have a good weekend. I'll see you next week.